Hey everyone, Ms. Kilroy here. Today we're going to do some notes and then you'll have the rest of the period to work on your classwork, and whatever you don't finish will be homework. So we're going to start with some C notes, so set up your page C note style. Periods 1, 3, and 5 go to page 79. Periods 2 and 6 go to 75. Set it up C note style, so that means the title at the top is velocity and acceleration. Our essential question is, what is the difference between speed and velocity, and how does it relate to acceleration? So this goes at the top. Underneath it, we have the essential question. On the left-hand side, set up a side for questions, and then have a summary at the bottom. And then we can pause this at any time if anybody needs more time, but I'm going to keep moving forward. Make sure you have this at the top and the essential question, and then you're on the correct page depending what period. All right, here we go. So our topic is velocity and acceleration, and we've been talking about these words for a couple weeks now, but now we're going to write them down. So what is velocity and acceleration, and how does it relate to the real world? Well, let's watch some football.
From big and bulldozing to small and speedy, NFL running backs come in many shapes and sizes. But to succeed at football, all running backs must excel at kinematics, the branch of classical mechanics that defines how objects move.
Because kinematics describes motion, it describes everything an NFL running back does, basically, which is his motion up the field as he tries to score.
Kinematics uses three concepts to define motion: position, velocity, and acceleration. Position defines location within a space, such as the surface of a football field.
Position would be a running back's location on the field, and he can change that with his motion.
In this play, let's define the running back's position where he takes the handoff. After executing the play, however, his new position is his opponent's end zone.
The position relative to the goal line changes the set of options that the running back has in terms of the direction he chooses to run.
A second kinematic concept is velocity, which describes both the direction and speed of the running back. In the NFL, one-way speed is measured is a player's time in the 40-yard dash.
A long time ago, almost right at 10 years ago, my 40-yard dash was 4.26.
To help illustrate the concepts of kinematics, Deuce McAllister, all-time leading rusher for the New Orleans Saints, ran the 40-yard dash in front of a high-speed Phantom camera.
You want to stay low as possible while running the 40, particularly the first 10 yards. So it's literally like you're being shot out of a cannon.
Using McAllister's personal best in the 40, 4.26 seconds, it's easy to calculate his speed. Divide the distance by the time to get his average speed, 9.39 yards per second, or 28.17 feet per second. To define the velocity, simply add a direction, 28.17 feet per second north.
When we talk about speed, we're talking about the magnitude of velocity, and then its direction is dictated by where the running back goes.
On the field, great speed is used to elude tacklers.
When you have speed and you have very good speed, that 5-yard play for most backs becomes a 50-yard play.
Also helpful is the ability to cut or suddenly change directions.
That helps you make moves against a defender. That helps you stay free from getting tackled.
Beyond position and velocity, the third kinematic concept is acceleration, which describes how fast speed is changing.
You never know when you may need to hit that button, per se, to accelerate at maximum speed.
To understand acceleration, consider again McAllister's 40-yard dash. While his average speed is 28.17 feet per second, his instantaneous speed varies. He starts with 0 speed and then increases his speed or accelerates until he reaches a top speed, let's say hypothetically 31.5 feet per second. If we know how long it takes McAllister to hit his top speed, let's assume 1.2 seconds, then it's possible to calculate his acceleration as the change in speed divided by the time.
Acceleration is the change in velocity per unit time, which if we compare it to velocity was the change in distance per unit time.
In this case, 31.5 feet per second divided by 1.2 seconds means that McAllister's acceleration was 26.25 feet per second squared.
We want to reach our top velocity as quickly as possible. Someone with very low acceleration might take 5 yards to reach top velocity, while someone with great acceleration might be able to reach top velocity in half that distance.
On the playing field, acceleration, or the ability to reach top speed quickly, may be a running back's most potent weapon.
If you can accelerate, you're going to get to top speed, even if your top speed isn't as fast as the guy that's faster than you. You're going to beat him to his top speed. Therefore, you're going to be more successful than he is.
Without kinematics and its concepts of position, velocity, and acceleration, NFL running backs would be easy prey, and football itself wouldn't be nearly as fun to watch.
All right, so let's go back to the notes. So the first word we just learned about was velocity. And velocity is just speed in a given direction. Go ahead and write this down, please. Everything in red. So velocity has two parts. It has the magnitude or the size, or which is the number. So for example, you're traveling in a car at 65 miles per hour. Well, the 65 is the number or the size, how fast. And then the only difference between speed and velocity is that velocity has a direction. It's telling us where it's going. So if you say a car is going 65 miles per hour, that's a speed. But if you say it's going 65 miles per hour north, that's now a velocity. Or if you have in the positive or negative direction. So for example, 70 kilometers per hour northwest or 40 meters per second to the right. Now, in our position versus time graphs, we calculated that there was a negative speed. What does that negative speed mean? It meant it's coming back to where it was. So there was a negative. So that was telling us the direction. So it was actually the velocity. Okay, go ahead and write this down. So this part you guys already know. You guys should know what velocity is, just speed in a given direction. And then if I'm going too fast, feel free to pause it, but I'm going to move on to acceleration. Acceleration, all right. Acceleration is just a change in velocity over time. So, for example, if you're starting on a roller coaster, you're sitting in your chair, you're ready to go, you're going 0 miles per hour, and then when it shoots you out and it starts going 70 miles per hour, that change from going from 0 to 70, that's you accelerating. So I think you guys are pretty familiar with that, like acceleration by speeding up a car, changing the speed that way. But we can also change the velocity by slowing down. So when your parents slam on the brakes and you make that sound, so you're going from 30 miles per hour to 0, that is also accelerating. So it's kind of a weird way to say that we're accelerating when we're slowing down, but acceleration is just when we change velocity. So we can change velocity by speeding up, slowing down, and then the last way is if we change direction. So again, in this roller coaster, how they're doing loops and they're going all which way, they're changing direction, so they're constantly accelerating. Okay, make sure you write all of this down. Also in the football example, when they were cutting, so they were going straight and then they cut to the left, that also counts as accelerating. So when you're changing your direction. Again, if I'm going too fast, you guys can pause it so everyone can catch up. And here's an example. I want you to write all of it down, everything, even this question. So a car increases its speed from 30 miles per hour to 45 miles per hour in 5 seconds. What is the car's acceleration? So remember, miles per hour. Okay, I want you to write it like this, please. Write down this whole question. And the first thing we're going to do, just like the 4-step method, we're going to circle what we know. It's not what I wanted. No. All right, so I kind of gave you this answer here, but the first thing that we do is we circle what we know. So 30 miles per hour is the initial speed, and we go to 45 miles per hour, which is the final speed, and it takes 5 seconds. So what we're looking at is the difference. How much did the speed change or the velocity change? So they started at 30, went to 45. So the difference in the speed is 15 miles per hour. And then the second thing we know is the 5 seconds. So please write this down exactly like this. Speed equals 15 miles per hour. Time equals 5 seconds. The second step, we write our formula. Our formula for acceleration is the change in speed over time. Let's see if I can write this down. Nope. So you could write the change in velocity over time, but to keep things simple, I'm going to keep it as speed. So we're looking at the difference in the speed over the time. So they increase their speed by 15 miles per hour, then we divide by 5. So that's our third step, plug in our numbers. And then the fourth step, we write our answer with units. So the units for acceleration are kind of weird. Our answer is 3 miles per hour per hour. Or you can write it as 3 miles per hour squared. Okay, make sure you have this down because you will be having to do these problems either today or tomorrow, so be prepared. It is the 4-step method. You write what you know, you write the formula, you plug in your numbers, and you write your answer with units. All right, for the rest of the period, you guys are going to be working on C notes. So that means I want you at your desk, silently working on, out of the textbook, answering the questions. The textbook pages are on the worksheet, and you have the rest of the period to answer the questions. Whatever you don't finish will be homework. All right, good luck. Thank you for being quiet.